Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. In today's video, we're going to continue where we left off. Remember, in the previous video, we did work, under work, energy, and power. So in today's video, we're going to be doing energy. All right, now, first thing, let's just identify the types of energies that we have. Remember, under energies, we have two types of energies. If you can remember from grade 10, we have two types of energies, namely the kinetic energy, as well as the gravitational potential energy. Gravitational potential energy. All right, let me do this. Yes, gravitational potential energy. Now, we know that a kinetic energy, we say it is what? We know that we say kinetic energy, it is the energy an object has as a result of the object's motion. Again, remember, an object has kinetic energy when it is in motion. Again, when it is in motion, it has what? Kinetic energy. Again, then we know, as per definition, gravitational potential energy, it is the what? It is the energy an object possesses due to its own position relative to a reference what? Reference point. I won't write down those definitions because definitions, you should take them directly from the exam guideline. Yes. Now, let's talk furthermore about kinetic energy a little bit. Remember, you are given the formula for kinetic energy as EK, or just K. It is equal to, but I'll just use K for all my videos. You can also use EK. It's a matter of preference. Kinetic energy, it is given as half mv mb squared, where we know m, it is our mass measured in kilogram. I repeat, I also mentioned this on our previous video that in physics, we measure mass in kilograms, but in chemistry, we measure mass in grams. Then we also have what in our formula here? V. We also have V. V, it is our what? V, it is our velocity. Remember, velocity, it is measured in meters per second. Then K, it is our kinetic energy. Measured, remember, any form of energy, it is measured in what? In joules. Again, yes. Then when we come to potential energy, we know that it is given as EP or just U. But for the whole of energy problems, I'll be using U. It is equal to what? mgh, where mass, it is still the same mass in kilograms. G, it is our gravitational acceleration constant, or on Earth specifically, meters per second squared. Then we have H. H, it is our height. This is very important to take note of. This height, it is a vertical height. It is measured in meters. Then we know that U, it is our potential energy. Potential, I'll just say energy, measured in what? In joules. Those are the basic equations that you'll have to know. We are going to use them a lot when we go to conservation of mechanical energy, as well as work done by non-conservative force, as well as work energy theorem. All right. With that being given, let's come here. Now, All right. Now, as per exam guide, we are told that we are gonna be dealing with work energy theorem. Now, work energy theorem has a definition. It states, it says like, state the work energy theorem as what? As the work done on an object by a net force is equal to the change in object's kinetic energy. Preferably, I prefer using the the second one. Let me see. Let's see what the second one says. It says the work done on an object by a net force is equal to the change in the object's kinetic energy. Well, if I see very well here, these definitions are more or less the same, but all right, I think the definition that they were supposed to put here was this one. That says sorry, that says the network done on an object is equal to the let me erase this, to the change in kinetic energy of an object. Yes, so it says now the network done on an object is equal to the what? To the change in kinetic energy of an object. Now, the reason I prefer using this formula that I wrote down here for you is because it is very easy to extract this definition from our what? From our mathematical representation of this this theorem. Now it says W net, it is equal to change in K. Here we are given here W net it is equal to change in K. Now why I prefer using this? Because I can say the network done on an object is equal to the what? To the change in kinetic energy of an object. You see why I prefer using this definition. It is also correct. I think the exam guideline, there was a mistake in terms of putting another definitions there, because if we both see this are more or less the same definition, it is the same thing. So yes, the second definition, it says the net work done on an object is equal to the change in kinetic energy of an what? Of an object. Yes. I'll just remove this. Now, the second bullet, now we have stated this is easy 2 marks, level 1 type of question that everyone must get. I always emphasize that definitions, everyone must know them all of by heart. Apply the work energy theorems to objects on horizontal, vertical, and inclined plane for both frictionless and rough surfaces. All right, now let's make an example. One example. Let's start with the basic example. Let's say here we are on a rough surface. Remember, when you say a surface is rough, it means we have what? We have friction. Again, let's say I have my applied force in that direction. Let's say my object is displaced towards the right. My object is displaced towards the right, changing x 10 meters. Then after a certain time, here is my object, M. Again, now let's say this car of ours here, or rather the block, has an initial velocity of 5 meters per second. Fair enough, right? 5 meters per second. Now, we know that this object is going to be moving on a rough surface. So there will be a what? A force of friction. That's what that opposes the motion again. Now we know if this velocity initially was 5 meters, as it goes through this rough surface, what will happen to our velocity? Our velocity will decrease. Let's say it finally reaches, it stops after 10 meters. After it, oh, I want to change a color to red. After it has traveled 10 meters, it now comes to stop. V final, it is equal to 0 meters per second at rest. Remember, this is a keyword. When something it is at rest, it's in a velocity, irrespective of whether it is initial or final, but the velocity, it is what? It is 0. Then the initial and final, you are the one who will assign that. All right. Now, let's say we want to calculate. Let's say we have a force, applied force of 50 newtons here. 50 newtons, not 50 watts. 50 newtons. Now, let's say the question asks us to calculate the frictional force. F. Now, here is a question. Calculate what? Frictional force. Now we're going to use what? Remember in our last video, we learned that to find frictional force, or rather to calculate work for frictional force, it is W, it is equal to the force multiplied by changing X, therefore cosine of an angle. But in this case, we are not given the work that this friction does on an object. Again, so now you have your initial velocity of 5, you have your final velocity. Therefore, it means this object, as it goes through this rough surface, it loses what? Energy. But what kind of energy that we are talking about that this object loses? It loses kinetic energy. Because why? Because its velocity moves for starts from 5 up to 0. Now energy is lost in there. Okay, due to what? Due to frictional force. Yes, because it is doing what? It is opposing the motion. Again, all right. Now let's try to attempt our calculation. Let's try to attempt. But yes, so we are going to use W net. It is equal to changing K. Now, W net refers to all the forces. It is the work done by all the forces. Because why? W net, remember when you calculated W net in our previous video, we said it is equal work done by friction, work done by applied force, work done by all those tension forces or whatever forces again. So now, it means here we are still going to apply the same thing, but in this case, we're going to substitute on this side again. So it's going to be work done by applied force plus work done by friction. It is equal to what is changing K? Remember, changing K, it is K final minus K initial. Remember, anything that has to do with change, it is K final minus K initial. Then let's see. What is work? We know that work, it is whatever the force that we're talking about. In this case, it is FA, changing X cosine of our angle, plus what? Frictional force, changing X cosine of our angle. It is equal to, what is K final? K final, it is half mv squared, but in this case, it is final. Then half mv squared initial. We agree? Yes. Then now applied force we have. Oh, remember another thing, applied force is gonna have an angle of 0 degrees. Why? Because we see that our object is displayed towards the right. Our object is displayed towards the right, but as well as our applied force, it is acting on an object while moving towards the right, or it is trying to make an object to move towards the right. So we are saying our angle for FA, it is 0 degrees. Then for our friction, it is how much? It is 180. In most cases, I think 99% of the time, I'm scared to say 100%, but yes, 99% of the time, frictional force, its angle is gonna always, it's gonna always be how much? 180. Why? Because we know friction by definition, it is a force that always opposes the what? The motion. So every time our frictional force, it is always going to be how much? 180, its angle there. All right? Because if our object were to move in that direction, then it means our friction was going to move in the opposite direction. So yes, it's still the same thing. Frictional force, it's always 108. All right, without wasting any further time, let's just substitute our values here. Now, what is our applied force? Our applied force, it is 50 newtons. What is our change in x? Our change in x, it is 10 cosine of 0 degrees. I repeat, when you substitute FA here, you only substitute the magnitude. We know that F8 is positive, but in this case, we do not care about the positive. We just ignore the sign in front of our force. Why? Because as per definition for work, it says it is the what? It says is the product of the magnitude of the force and the magnitude of the displacement. Again, now do not put a minus here. I'm even scared to do it. Do not put a minus here and say, no, frictional force should be negative. No. This cosine of something will take control of the what? Of the sign. Yeah, friction in that case. So we're gonna continue by saying plus friction, then multiply by displacement, cosine of 180 degrees. Then half, I don't think I gave mass to that object. Let's say it has a mass of 2 kg. 2 kg. All right, let's substitute 2. My final velocity, it is 0. Why? Because it came to rest. I get minus half 2. This is 2. My initial velocity is 5 squared. Then I have a 5 multiplied by 10, it is 50. 500 plus cos 180, it is equal to -1. So it's going to be -1 multiplied by 10 multiplied by this force. Then it's going to be how much? -10F. -10F. It is equal to, this is 0. This goes away to 0 because why? Anything multiplied by 0, it is 0. Then we are left with minus what? Half multiplied by 2, that's 1. Then 25 minus 25. Then you do your mathematical gymnastics there. Let's see. Let me take the 10F to the other side. Then I have 500. Then I take this -25 to the other side. It's going to give me 525. Therefore, my frictional force there, when I divide both by 10, it's how much? If my math is still good, 52.5 watt newtons. Again, now it is very, this answer is very reasonable. Why? Because this friction, our friction, we are saying we calculated as 52.5, and our applied force, it's how much? It's 50. So we agree on this force is greater than our applied force. Why? Because this is 52.5, this is 50. Hence, now our object at the end of the day ended up doing what? Ended up being at rest. But if our applied force was greater than our friction, our object was going to move until someone intervened and stopped it. Again, yes. Now, I think I'm done explaining W net, change in K. It's very easy. Just identify all the forces that are acting on your object. Actually, most importantly, identify all your horizontal forces or parallel forces. In this case, we had FA. We also had what? Frictional force. These are our only horizontal forces. And remember, horizontal forces or parallel forces are the ones that are doing work. We know we have normal force as well as FG, but we do not include them when we calculate what? Work. FG, we are going to include it when we are dealing with an incline. On an incline, remember, we have something like this. Okay. Then let's say we have our applied force. Let's say it is frictionless, our slope is frictionless. Then if it is frictionless, there is no friction. Then we know we have Fg going down. Then we know normal force perpendicular to our object. Then here we're gonna have what? Nothing, no friction. But now, as our object, let's say our object is displaced towards up the incline. Now, what's gonna happen? What's gonna happen is that this parallel component of Fg, remember Fg can be broken into its components. Fg parallel and Fg perpendicular. This is Fg parallel. Now, this Fg parallel is the one that is trying to make the object to move down. Let's ignore this for now. This Fg parallel is the one that is trying to make this object to move where? To move down. Now, when we calculate work done by this energy, it's going to be W net. It is equal to what? Change in K. Let's say whatever the initial velocity and the final velocity there, yeah, whatever the case. We know, but when we substitute W net is going to be what? Work done by applied force plus work done by Fg, not just Fg, parallel. This is very important to take note of. I still repeat my statement. Fg on its own does not do any work, but the parallel component of it, which is Fg parallel, is the one that is doing work. Why? Because we said, or rather I said, parallel forces or parallel components of forces are the ones that are doing what? That are doing work. I avoid using horizontal because in this case, it is not necessarily horizontal, it is on an incline. But when I say parallel, I know it is parallel to what? To my slope there. Again, so yes, the only time that you're going to include Fg when you calculate the work, it is when you have its component. All right. I hope that's clear. If it's not, we will still have a video. I think 3 videos doing question papers, past question papers about this topic of work, energy, and power. Before we move on to another topic. Now, let's come here. Our exam guideline, it says after doing WNet, now we can move on to doing what? We can move on to doing conservation of energy, as well as what? As with non-conservative forces present. Now, before I go to non-conservative forces as well as conservative forces, I think I'd start here. Here we are defining, I'll start here to stating the conservation of mechanical energy. I'm going to do them, all of them today, so do not worry. Conservation of, this shouldn't be new to you because you did this in grade 10. Conservation of mechanical energy, but it's fine if you have forgotten about it, it's fine. Conservation of mechanical energy. You should know it as per definition. It says straightforward, this one. Very straightforward. It says the total mechanical energy in an isolated system remains constant. I repeat, the total mechanical energy in an isolated system remains constant. Now, ignore this thing inside the parenthesis that says sum of gravitational potential energy and kinetic energy. Remember, mechanical energy, it is there, yeah, EP plus EK. So just ignore this part. You do not need to write it. When you have said mechanical energy, you are fine, but it should be the total. Then we have a note: a system is isolated when the net external force acting on the system is zero. That one, I will come to it. Yeah, this point, it is very important. It is a definition also on its own. I think when dealing with momentum, conservation of momentum, this definition is very important. The isolated system. But all right, we have defined what is conservation of mechanical energy. Now, mechanical energy, it is given by changing, or rather, not change. It is given by kinetic energy plus potential energy. Remember, I said it is also fine to use EK plus EP. It's still the same thing. Now, mechanical energy, it's the sum of my kinetic energy as well as my potential energy. But now, when I conserve it, it means when, in whatever the scenario that I have, my mechanical energy between two different points does not change. Right? Someone is saying, I do not hear this. It's fine. Let's do an example. An example. Before I do an example, I have to take to note to make you aware of this. This is very important. The formula for conservation of mechanical energy is this: mechanical energy at the top or at point A, it is equal to mechanical energy at bottom or at point B. This formula you only apply when there is no, I want to say, external forces. What are external forces? External forces are forces such as friction, applied force, tension force. These are external forces. If my object has any of these, or rather, if my scenario has any of these, this formula is not applicable. It is only applicable when there is no external forces. If there are, you can use W net work energy theorem or other forces such other equations such as a non-consecutive force, which we will go to just after this. Now, I think it's clear that we use it only when there is no friction. Let's say we have a scenario here. Let's say I have a scenario. I want to make it straightforward or better explanation. Let's say we have our angle here, alpha. Then this is my height. Remember, I said for the formula of MGH, it should be a vertical height that you are dealing with, not just any height. Then here, let's say it travels whatever that distance. Okay. Then here is our block, initially from rest. From rest, we know if it is from rest, initial velocity, it is equal to 0 meters per second. Then it travels there, then it reaches this point with a velocity final, v final, not u final, v of 2 meters per second. Now, mass m, mass M. All right, let me do this so that you can see we're not talking about different object. It's still the same object, but it has changed the position now. Now, one might ask, for how? There's no applied force, so how is this object moving down? Then let's draw our free body diagram so that we can see. Remember, it is on an incline. You can do this so that you can identify all your forces. This is my normal force perpendicular. My FG always acts downwards, remember? Then now, how? They are the only forces that I can identify. No frictional force. This is frictionless. Frictionless. Take note, it is frictionless. So there's no friction, there's no applied force, there's no tension. Now, what causes our object to move down? Remember, this force of Fg can be broken down into what? I think it should be straight. With the normal force, it should be equal to the normal force. Right, it's fine. But make sure it goes like this. It's fine. It should be equal to our normal force. Then we have this other component of Fg that always moves downwards. Fg parallel. Now, how? In this case, remember, I did it. It was going in this direction. Remember, wherever is downwards in your scenario, it is where your Fg parallel will go. In this case, here is my downwards. Downward is moving in that direction. So it means my Fg parallel will be moving in that direction. So now, what are the forces that are going to be doing work? The forces that are going to be doing work, let's ignore this, are the forces that are acting parallel. Parallel. Interesting. This is only Fg. Fg is the only one that is acting on my object. Now, it means now I can apply my mechanical energy. I did not even need to go through this, but for you realizing that there's no friction, there's no tension, there's no applied force, you should come here, immediately come here. Let's say this is point A, then this is point B. Now mechanical energy at point A, it is equal to mechanical energy at point B. Now mechanical energy at point A, remember what is mechanical energy? It is K, kinetic energy at A plus potential energy at A. It is equal to what? Kinetic energy at B plus potential energy at B. Sorry. Let's say here, our height, it is 0. Our vertical height, let's say it is 0. Yeah. Let's say it is 0. So if it is 0, when you start substituting, remember, Ka, it is half. It is half mv squared at point A plus mgh at point A, half mv squared at point B plus mgh at point B. Again, now you realize that at point A, what is happening? Your velocity, it is 0. Remember, I said it is moving from rest. So if your velocity, it is 0 there, it means you won't have kinetic energy in that matter thereof. It means at A, there's no what? There's no kinetic energy. So this falls off. Then H, we have a vertical height that is given as H. So it's going to be mgh. We are not substituting. I won't be doing any calculations. I'm just explaining the concept. Then half mv squared B. At B, we have a velocity. So it's going to be half mv mv squared at B. You'll substitute the value you have here. Again, plus this is going to be equal to 0. Why? Why I'm saying it's going to be equal to 0? Because our height at point B, it is equal to 0. So everything multiplied by 0, it is 0. So it's going to be 0 here. No need to write this. But you can also substitute, because sometimes they want you to substitute to show your substitution. So let's say the question was calculate height in meters, of course. calculate height in meters, our question. So we are going to say, all right, when we substitute, it's going to be mass. Let's carry on with our mass of, let's say our mass is 2 kg. So let's say it is 2. What is G? Remember I said G, it is gravitational acceleration that is constant. 9.8. My height is what I'm looking for. I have my mass is 2, then 2 squared. Okay. When I substitute there, I do my mathematical gymnastics. I get that my H, it is equal to, this is 1, then this is 4, divided by, I think this is 19.6. Then whatever your calculator gives you there, I'm not sure. It gives you how much? Let me see, approximately 4 divided by 20, it is 1 divided by 5. More or less something like 0.1. Let me do this. Let me not say equal. Remember, I'm approximating here. Approximately 0.19, maybe. You can just do your calculations on your calculator there. I did not say it is equal. I said it is approximately. But when you have your calculator there, when I punch my calculator, it gives me how much? 19.6, 0.2, which is true. Which is true. It is 0.2. This is true. 0.204, but yeah, 0.2 meters. Why? Because I approximated 4 divided by 20, it is 1 divided by 5, which is 0.2. So anything close to this, it is okay. All right. Now I can say it is equal. Now let's move on. I think we are done with mechanical energy. Every time when you have no friction, whether your object was moving from this point and was projected downwards, and then reach this point A, point B, point A, point B. Here we have our vertical height, meaning here we have MGH. Potential energy, it is there because we have a vertical height again. But here, our MGH, it is equal to 0. Why? Because our height here, it is 0. Again, but the final velocity here, let's say it is whatever Vmax. Then here, let's say it is released from rest, projectile motion, released from rest, initial velocity is 0. Now, if my initial velocity is 0, what happens to my kinetic energy? My kinetic energy, which is half mv squared, will equal to 0 because my v here, it is 0. But here, since when I have my Vmax, it means it's going to be a half mv max squared. So you see, no friction, no air friction, no air friction, no air friction, no applied force, no tension. We did not say there was a force that was applied. No, it is moving under the influence of gravitational force only. Gravitational only, gravity only, throughout the motion until it reaches, before it reaches the ground. All right. Even here, mechanical energy, it is conserved if there is no friction or any external force. Now let's move to conservative and non-conservative forces. Now, let me start with conservative force. Conservative force. As per definition, conservative force, we are saying are the force for which the work done in moving an object between 2 points is independent or does not depend on the path taken. Let's check the exam guide. Ring. Define conservative force as a force for which the work done in moving an object between 2 points is independent or does not depend on the path taken. The example that we have is gravitational force, the elastic force in a spring, and an electrostatic force. But in this case, we are going to focus only on Fg. Let me explain why we are saying Fg, it is a conservative force. I won't just mention anything and not explain why we are saying that. We are saying this is a path independent. I'm not sure if my independent is correct. If it's not, sorry. I'm teaching physical science and mathematics, not English in that particular matter thereof. All right. This is path independent. This is not a full definition. It's just for explanation purpose. No, now let's prove why we are saying a gravitational force. It is an example of this conservative force. Now, let's say we are moving on this surface here, smooth surface. Let's say we have an applied force, no friction. It is displaced towards the right. I will only talk about Fg. Other forces are present, but I will only talk about Fg. Check Fg. Where does Fg act upon this object? It acts downwards. Okay? All right. Let's have another scenario where we have our block on a rough surface. On a rough surface, meaning there is friction. And let's say it is moving in this direction. I do not want to use right always. Let's say it is displaced like this. This is our change in x. Then it means our frictional force is going to be moving in that direction. Where is our Fg acting? Again, Fg is moving downward. Whether my object it is moving towards the right or towards the left, my Fg always acts down. Let's prove use another scenario. Another scenario, I'm moving on an incline. Here's my object. Let's say it is moving upwards and it is displaced upwards. My change in x. Now, whether there is friction or not, that does not matter. Where is my Fg acting? If this is my block, where is my Fg acting? Downwards. It is acting downwards. So irrespective of the scenario that I'm having, my Fg always acts downwards. So hence we are saying Fg does not depend on the path taken. Let's say this is projected, our ball is projected up to this point. Above this object, where is it? Let's say here is our object. Let's say it is in free fall. This is very important, I should mention. In free fall, meaning only gravity acts on the object. But this gravity acts where? Downwards. Bompo. What are you saying? I'm saying gravity always acts downwards. So when you can see in scenario 1, it was moving downward. Scenario 2, downward. Scenario 3, downward. Scenario 4, downward. This means it is a conservative force. Why? It does not depend on the path taken. Whether you are on bed, whether you are, I don't know, in space, it is always acting downwards on an object. I hope that's clear. They like to ask this question, okay, identify the conservative force that you can identify. Every time when they just say conservative force, Fg, gravitational force. Easy one mark. Easy one mark. Fg is your conservative force. All right. Let's move now to non. I'm opposing my statement now. Non-conservative. Conservative. I hope my spelling is correct. Force. By definition, my non-conservative forces are the force for which the work done in moving an object depends on the path or is dependent on the path. Remember that one was independent. Conservative force was independent. This one is dependent. Let's check the exam guide. It says define non-conservative force as a force for which the work done in moving an object between 2 points depends on the path taken. Example of frictional force, air resistance, tension in a cord, and all of that. I'll just write them again. Let's go back. Let's go back. Now, this is path dependent. It depends on the path taken. Yes, it depends on the path taken. Why? All right. Examples of this, we have friction, tension, applied force. Applied force. Okay. Now let's check a scenario to prove this. This is rough. Applied force is placed towards the right. This is my mass. Let's talk. I'm no longer talking about FG. FG is not a non-conservative force. We have already proved that FG is a conservative force. Normal force. Do not talk anything about normal force. I did not mention anything about normal force. Do not try to be smart and say normal force, it is a conservative force and what you are gonna be wrong. Because, never mind. Normal force does not classify under a conservative or non-conservative force. All right. Even if I can classify it under non-conservative force, at the end of the day, it does not do any work. So I do not care about it. Now, if I'm moving towards the right, where's my friction going to move in this case? Towards the left. Right. All right. Okay. Where are you going with this? I'm coming here. If I have my second scenario, but in the, still free, this is not water. This is my rough surface. If my applied force, it is applied in that case, and my object, it is moving towards the left, where is my friction going to move? Towards the right. These two cases are more or less similar, but now what changes it is the displacement. This it is towards the right, this is towards the left. But look, if I displace my object towards the right, my friction moves towards the left. If I displace my object towards the left, my friction goes towards the right. So it means now my friction is classified under what? Non-conservative force, because it depends on the path taken. If my path is going towards the right, my frictional force, it is opposing. If my change in x, it is towards this direction, it is opposing. So it is path dependent. It depends on the path taken. Again. Yes. So this is very, very straightforward explanation. It is a very, very straightforward explanation. Now, unlike a conservative force, we have a formula for non-conservative force that says it is a change in kinetic energy plus a change in potential energy. Now, let's have a scenario. My height, vertical height. Let's say my object moves from this point with an initial velocity of 2 meters per second, then reaches down with a velocity of, because some people are going to say you are dealing with two objects. It reaches the ground, or whatever, with a final velocity of 5. Yeah, 5. Let's say 5. Or let me just substitute. Let's say this is height. Height, how much? 10 meters. Then we have our angle there. Then remember, it is moving in that direction. This is our change in x. 8 meters. Yeah, again. So now, we are missing other forces. Let's say it is moving on a friction, on a rough surface. It has friction that opposes the motion. Then there was an applied force. Or even if you do not include applied force, but let me remove it. So here I have what? I have just only friction. Again, but now what causes my object to move down? It is a parallel component of weight of Fg. Remember again. So yeah, remember I did a scenario like this when I was explaining mechanical energy, conservation of mechanical energy. But for conservation of mechanical energy, there was no what? There was no friction. There was no what? There was no friction. Hence, I was able to apply conservation. But now, immediately when I'm told it is on a rough surface and there is friction, I stay away from mechanical energy, conservation of mechanical energy. I just put it aside, that formula EU. Again, yes. So here, I can use what? I can use this force, this equation yaka incha that says, all right, I can see there is friction, and I classified friction as what? As a non-conservative force. Now, let's agree that my object is going to be under the influence of, sorry, Fg parallel, Fg perpendicular. Uh, where's my thingy? Here it is. Normal force as well as my friction there. All right. Again, remember I avoided saying I know my weight acts downwards. I know. But in this case, I broke it into its components. So yeah, hence I did not include it. We know that it is always acting downwards. All right. Now, when I do my work done by non-conservative force, the question is, yeah, this is interesting. Sorry. This is interesting. What are non-conservative forces? I know it can only be when I'm dealing with friction, tension, and applied force. The work done by these forces, But now I can see on my parallel surface. Now my parallel components there are what are Fg parallel as well as friction. But can I include Fg parallel here? No. Why? Because Fg, it is not a non-conservative force. Fg, it is a conservative force. Therefore, it will not be included here. The only thing that you will include here, it is what? Work done by friction. Because friction, it is what? Non-conservative force. Then I say, what is a change in K? You know, it is your half mv squared final minus, let me do this, half mv squared initial plus change in potential energy. It is mgh final here down minus mgh initial there. Again, then you can calculate, you know, this is the same as frictional force, change in x, cosine of my angle. It is equal to also this one, you bring it down, then you substitute and calculate for whatever value that they require you to calculate. Again, yeah, that's all. Another important thing, all right, let's take a recap on our formulas. We say the formulas that we have, it is, we started by work, it is equal to force, change in x, cosine of an angle. Then we went to W net, it is equal to change in K. Then we went to non-conservative force. Then we went to mechanical energy at A, it is equal to mechanical energy at B. These three given on your formula sheet. This one, you are not given. It's a must know. Must know it by heart or by brain or by whatever. You must know this one. You are not given. Again. So now, each and every has a condition. You use this when there is no what? friction, applied force, tension, tension. This one is applicable everywhere. This one. This is the master. This is the master. Whether you have friction, you have no friction, yes, you can use this everywhere. Everywhere it is applicable. Then we know this one. There should be what? Friction. Applied force. Any of these. Applied force as well as tension. These two are opposing each other. This one and this one, they are opposing each other. Okay. But this one, everywhere, it is applicable. All right, thank you very much. I think we have reached the end of our video. So yeah, if you liked the video, please give it a thumbs up and kindly subscribe to our YouTube channel so that you can be updated on the next video that we are going to upload or dealing with power. Then we end that topic of work, energy, and power. Then I will do 3 question papers, or rather 3 questions related to work, energy, and power. Then we move on to another topic. Thank you very much for your time, folks. I hope you enjoyed the video, and if you did, please give it a thumbs up again and kindly subscribe, and also add your friends or recommend the channel to your friends.